Back again. Too soon, but too bad. Sorry. Yeah, sorry. There's a lot of content, and some of it is not very precisely focused, but I think a lot of these arguments need to be made, and some of them obviously have to be made over and over again before people start to pay any attention. So, the Robert Ritchie guy, who, like I said, this is like the other guy, the other British guy who that does all the sound experiments and stuff, who probably is having health difficulties again or something. But anyway, I don't know. I haven't heard from him in a while. But anyway, regardless, it's great stuff. I wish I had a better lab. Better, maybe when I move. That might be a positive benefit, but who knows? I probably won't have space either, so who knows? But anyway, he's made a new video with the rotating disc thing, and again, I did sort of talk about that, but see, that's sort of an interesting subject, right? This whole idea of how the force is transferred and gyroscopes and how they function. And it's all been left rather mysterious. I mean, I could show you a bunch of videos by the guy who sort of invented the maglev train idea, but didn't really get credit for it. The British guy. Making it all very mysterious, when it's not all that mysterious, I don't think, in the sense that, if you could actually put a bar into the center of the sun and have it connect right to the center of the sun's gravity, you sort of understand that would be a powerful thing, in terms of any movement would be backed up by a ton of mass. So it'd be like really heavy things moving, and nothing could stop or prevent the power of that energy. It would have to be translated into something. You couldn't just ignore it. It would either crush something, or you have to convert the energy into some other form of energy. But the energy would be unresistible. It would be an unmovable force kind of thing. Anyway, the opposite of unmovable. Guaranteed to move. And so you can sort of see that with this whole idea of something spinning. The only way you're connected to it is through this bearing. And you can delude yourself into thinking, well, it's spinning so fast and there would be no friction on the bearings and blah, blah, blah. But of course there is. And of course there's more friction because of gravity on one side of the bearing than on the other side. That any kind of tilt or any kind of movement would create extra friction on the part of the bearing that was the one going to impose more force. So depending on how your bearing is made, obviously you could tilt something that's spinning. And while you're doing that tilting, you're forcing all the matter to change. So therefore you're imposing quite a substantial amount of force, in the sense that you have to actually move matter. And all that movement is really just happening through the bearing. So the bearing's making that much contact with the spinning. And therefore, as I sort of pointed out, the two things are going to resist. The thing that's spinning, the friction is about moving the thing that's not spinning. The two effects are indistinguishable. We're back to kind of a relativity argument. It doesn't matter who's moving. It just matters that the force is going to be translated. So the thing has to move the opposite direction from the direction the thing that's spinning, where the most force is hitting it. So if there's more force on the top of the bearing than the bottom of the bearing, then obviously this direction becomes important. If it's the other way around, then this direction does. And that's all there is to it. There's nothing more complicated than that. You're just feeling the effect of the fact that you are a movable force. There's more force being imposed than you can resist, or that gravity can resist, or it's a lot of force. So if you could actually do the experiment where you could know exactly where all the energy goes, you'd see that the wheel actually spins down. You're actually slowing the speed of the spin because you are imposing more friction, because you're translating it into movement of the axle. And that's all you're doing. You're changing the axle. You're putting force into the axle, just like a space shuttle or anything else, and it's moving in the opposite direction. All right. Okay, Gary, ran some math experiments. Yeah, I don't know what those are exactly, but okay. And now I agree with your force bit theory, and we'll put up a video showing my results and conclusions. Yes, well, let's not draw too hard a conclusion yet, but yes, thank you. It'd be interesting. I will show my perception of a magnetic circuit in the video. Okay, this, I kind of don't get this whole circuit thing. Magnets are clearly magnets are deflecting energy. That's the whole point of them. They can't work if they're not deflecting something to create north and south. So they're segregating something. But the idea of circuit, again, there's no need for a circuit. The whole way it works is not having a circuit. It's basically saying plus and minus. If I have a circuit, the plus shorts out to the minus. I need them to be different, not the same. I would like you to think about the possibility of adding spin to the force bits. Well, again, adding any kind of... See, spin is too non-quantized. Spin is too analog. It's too... You could have 9 million different degrees of spin, and that means you could add a certain little tiny fractions of energy by just adding a little bit more spin. And I'm just saying that the indications are that photons don't have that variability, that they are quantized. Kind of a boring clump, not a complicated clump. Be as critical as suits you. Well, again, I really don't. I'm not critical because it suits me, and I'm only critical in the sense that, like anybody who has done what we have done, which is lived and gained experience, there's certain things, I guess I can say, that I've been exposed to enough times to say I know a skunk smells like a skunk. So if somebody tells me skunks smell like, I don't know, long-eared rabbits, I'll just make the argument, no, it doesn't. Rabbits and skunks don't smell the same. Truth is like the pattern hidden on a rolled up carpet. Well, again, these more metaphors for how the truth is are cliches. Even I don't think is very useful in a sense. I still don't really agree that the truth is the problem. Finding the truth is not the problem. Getting past our bigotries and our biases and our belligerence in defense of our homies, in defense of what we've been raised to be. Our prejudices, that's simple. Our preconceived notions. That's the problem. The preconceived notions break the lenses and make us blind. We all need to unroll the carpet and see the truth pattern. Again, I'd say it's already unrolled, and again, so it's just not the problem. People are tripping over the truth all over the place and just ignoring it. The world is in a global warming crisis, lots of things, and the facts have been sitting there in front of them and they're not paying any attention. So what's the point? I mean, the facts aren't the problem. The willingness to accept the facts is the problem. Some people have their carpet unrolled more than others. Well, there's certainly people who have voice opinions based on just the merest casual book by the cover. And the book by the cover people, yeah, they're really a problem. Like I said, in the war, those are the first people you got to shoot, the people who can't make up their mind which side they're on. I am carrying out multiple experiments per week. Yeah, you really are, which is cool. Experiments are great. But as I will point out in a later comment here, is the trick with experiments is you really do have to do them. You really have to test the experiment. You can't just do the experiment one way and stop. You really have to push the thing all the way through. Okay, I made it to 19 minutes of this guy stopping and starting the video to fly off the handle in a jealous rage over outrageous notion that people might think that Nikola Tesla was a very intelligent guy. Now, I didn't make that argument, so again, that's just stupid. I just said that Nikola Tesla was not a great scientist, number one. His method wasn't proven in the sense that through time it was shown to have this huge flaw. Like I said, he was definitely somebody who had a preconceived notion, and he kept trying to conform the facts to his preconceived notion. And he was clearly way out of bounds on some subjects. Clearly he missed the whole nuclear bomb boat. He missed so many boats, right? Because he was obsessed with finding one kind of energy. The other one was found right under his nose, and he had nothing to say on the subject because, yeah, he was clueless that it existed. He didn't understand anything about the inside of atoms. How far can you go? Post your record here. So, yes, this is all very ha 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 ha, but you're not counter-arguing. The guy said a lot of things about Nikola Tesla that just weren't true. He didn't invent the electrical grid. He didn't do all these things that people say he did. A whole lot of people did that, including Edison. Okay, I mean, frankly, Tesla modified Edison's designs. Let's get who started the thing first. Let's get it in the right order. All right, he didn't invent these ideas, and you know, I mean, except for the three-phase motor. Okay, I'm just saying that most of it wasn't Tesla. It was a lot of people. All right, wow, this guy is so jealous of Nikola Tesla. So again, it's just stupid. Clearly, Tesla was insanely jealous of the popularity Einstein had, and he hated that, and that's why he had to insult Einstein. So I'm just saying, who was the petty person in this game is clearly Tesla. You know, and again, it was proven by fact, right? As soon as people stopped paying attention to him, he stopped doing physics. You know, spent the last 30 years of his life accomplishing nothing. He just called Nikola Tesla an elitist, bummy second-hand inventor. Yes. That's what he was. You know, he didn't spend too much time getting his hands too dirty. Sorry, bro, you got no cred. So, like, like somebody, like I would, Lucky Jester is his name. So, yeah, like I'm going to take that seriously. You know, that's like being called what? Profound, interesting person. No, that's, oh, troll. And then, sorry, bro, like, I'm your bro, which I'm not. I'm not your possession boy, you little inverted-dicked weasel. You anonymous, weak, cowardly weasel. You got no cred. Cred. Like, I'm going to play that game, too. No, homie, don't do that. Yeah, okay. Fuck you. Ugh. Alright, incomprehensible symbol that looks like a Christian cross, which is really annoying. Or two little stompy feet. I don't know what the fuck that is. I don't know why they allow people to have symbols as names, but whatever. Can you comment on this video? If so, I would appreciate it. Yeah, so I can do that. But maybe there's more comment here to do first. Should we believe the electrons are spinning around the nucleus with extreme speed? No, you shouldn't believe that. Or do the electrons stand still? I think it's more rational to understand that they vibrate a lot. So atoms are vibrating. So there is movement in them. But they're not going anywhere. Yeah, the spinning thing, like I said, it just doesn't work to try to connect things together. So if you're going to make Legos fit together, if they're all spinning, that's not going to fit together very strongly, right? I mean, the whole idea of the spinning pieces going through the atom, oh, there's a free electron bonding this atom together, and it goes all over, you know, it's not going to bind anything. You can't have the glue go all over the place. The glue's got to stay where the glue's got to stay to stick things together. So I think it just makes more sense to just go with a magnetic atom. It's not gravitational. Things aren't being pulled in by gravity, you know, and they're not being held, you know, by some magical force. It's all a real physical force, and the physical force is magnetism. And if you understand magnets at all, you can sort of understand that you can arrange them where they're positive and negative, the two poles, the north and south. You can create quite a bit of tension and keep magnets at bay. If you could create a world where they can't flip or do something, you could understand if I had them as monopoles. If I could break magnets in half and have actual monopoles, that I could arrange those monopoles in ways that would mean they can't really move out of their rigid geometry. Their geometry's holding them. They're getting pulled just as much as they're pushed away from each other, and they're locked in a tension. And it's just a much better theory, in my opinion. Hugely improved. And it makes why atoms bond make much more sense. Right. So let's. So this video. So these are interesting videos. You know, anytime you see these experiments on stuff, Browning in motion. What is that? Holidays video? Yeah, I don't need that one. So it should be this old crap. There's fucking ads everywhere. I hate it. I hate it. I hate it. All right, so that's the stupid retarded Higgs thing. I got to do that someday. So here we are with the electron.
With this apparatus, you will be able to see what happens.
All right, so in this example, we have an example showing what happens to electrons when they're a certain kind of a magnetic field, an even field. And I sort of explained the even field basically just means you're creating a synthetic kind of gravity. Let's see, where's the good picture of it? Move along, there it is. Okay, we see the circle. So we know that the electrons are getting pushed by a field, and they're moving not sideways to the field, but they're moving the way the field is hitting it. The field's hitting the electrons like this, and the electrons moving like this. So it's kind of an obvious. There's two coils. Two coils are producing a field going this way, and the electrons are doing the math. And so, so this video has some of electron, a nice little electron gun, and then you're going to put a magnet around and cause deflections. Now the problem with the way this is done, and I'm not saying it's done on purpose, but I just mean this is a fact though. They do these experiments, and they're sort of deceptive because this looks, see, the magnet's not going close, all right, and so you get this misimpression. So the idea is that the magnet is causing the beam to go down or up. So I bring the magnet in, and the beam doesn't go this way or this way. The beam goes up or the beam goes down. Well, yes, that's if you keep the magnet that far away. But you have to sort of understand what this beam is too, right? The beam is electrons. So maybe I'll draw this part just for clarity. Well, that's not much of a drawing. Where was that from? I don't know what that was. Hey, pretty horrible. Doesn't look like anything interesting. All right, so the whole idea is the electrons for an electron gun. Okay, they're getting shot out, but how are they doing that? Okay, well they're heating something. Okay, so they're creating a bunch of this infrared radiation, little force bits. And the little force bits are what's propelling the electrons. So you have to kind of understand that the force, okay, is going with the electron. So there's a beam of force that's coming out of the gun also. So these little bits of stuff moving the speed of light is flying with the electrons. So the electrons are in a beam of this invisible photonic energy. All right, that's pushing the electrons. All right, so you have two things. You have the negative electrons, and the only electrons you're seeing are the ones they have to maintain their velocity, so they have to still be going very fast to excite the hydrogen atoms in this. No, in this case they're using some other kind of argon. Well, anyway, they're using some other kind of gas, and so they have to be going enough velocity to excite the atom when they hit one. So there's little atoms in here, and some of these electrons will hit these atoms at a sufficient speed to create a photon that we can see. And so we're only seeing a select number of the electrons, plus we're only seeing, and we're not seeing the force that's actually propelling the electrons. So I just want to make that part clear. All right. So now this beam bends. You can see this. So it's bending down. We can't really see that. See, here's the edge of the front of the glass. So this gun is set up with with plates that allow you to deflect the beam. So this gun is made to do the deflection by an electronic means separate from an external magnet. So to understand, those plates are still there, and those plates can be just as influenced by this magnet as the beam itself. So you have to sort of understand that anything, if the magnetism can reach the beam, the magnetism can also reach the plates. So we don't know what part of this is the magnetism reaching the plates and causing them to become magnetic, and therefore bend the beam, or whether the magnet is where it is in position. So my argument would be is you have to think about the magnet as radiating, like a flashlight, but not a very good flashlight. Right, the radiation is coming out very spread, but straight lines. So clearly, if you have the magnet above the beam, the rays that are coming out straight, and then the rest of the rays are all at an angle. They get weaker and stronger depending on the angle that they're traveling, but it's an angle, clearly, from the magnet. So the magnet shoots straight, but it also shoots down, and it shoots up. So the first problem you have is, well, what happens if you have the magnet very low, and if you have the magnet very high? Does that change which way that beam will bend? Because the idea is you're going to try to bend the beam that way, away, with a magnet. Now the theory, right, logically you could say this becomes a distance problem, because I know the magnet gets much weaker with distance, the magnetism, right? So to push it away, I have to have enough magnetism, I have to be much further than the distance you need to be to make it move at all, right? So if you thought about the magnet, okay, let's draw it again. Okay, so if you thought about the magnet as creating a field, a force field of a kind, all right, then here's the end of the magnet. And think of it as it's creating like a force field that has a bow to it. All right, so that's what I'm trying to say. The radiation comes out of the magnet like this. And it's clearly strongest here in the center. Well, it's the same. It's pretty strong here and here, but see, it starts to get diluted by the other side of the magnet. Once you start going at these angles, the force becomes mixed color. So I should do that in red just to be precise. The red starts polluting as you get into these angles. All right, so the red's getting to it. So the pure force is here. This is the purest blue, which is the part that's pushing the electron away. So you have to understand the beam is here, and so you're coming in to push it, but we know that it gets, the strength is, let's see, just try to draw this with some relative meaning. We know it gets much stronger the closer you get by the inverse square law for a single pole. So as long as I have a single pole of the magnet facing something, it's going to be like the R squared rule in terms of the magnet's going to have pretty good depth, but it's still going to degrade by the R squared rule. And technically, if it was turned the other way, it would be the R cubed rule. So it's a pretty substantial degrade that magnetism has. It doesn't go very far without starting to get weaker and weaker and weaker. So the point would be is that you can have enough energy here to start pushing electrons, but you can't really push them that way because it doesn't have enough strength, so you're going to end up pushing them down. So they're kind of going to bounce off this curve, right? This is a spherical curve. It's a, all right, can I draw it spherical? It's a spherical curve, so it's a bowl. And so if we were to push into something with a bowl, you could sort of understand that the thing might just roll on the bowl, right? It's not going to get pushed this way, especially if it's getting weaker to go that way. From this magnet this far, I can't really push it that way yet. I have to get much closer to do that. So what it's going to do is start rolling off the bowl. It's rolling down off the bowl. All right? I think you can get that point. So, and what I would say is illustrating that. So you can find videos. I didn't really have time to go looking for them, but you can find other electron guns where the guy puts the magnet right on the surface, right up to the glass. And you'll see the electron beam fly right into the magnet or fly away from the magnet. So you get a clear understanding that it is repulsive. So what I'm saying is when you look at this, you have to understand that this idea of it going down and going up is a consequence. I think that's, yeah, here's another image of it down. See, so he's bringing it in and it's going down. Well, what it's really doing is just rolling off the board. It's rolling down to go around the bowl of the strength of the force. The force isn't strong enough to push it this way. It's only strong enough to push it, to let it slide down. So you could almost see it as an invisible bowl you're pushing in there, and as you push it in, you're just pushing the beam down. And you also see the arc of the beam is sort of an indication of that, because the further away you are, the less pushing you're getting, and the over at the other side, Yeah, I don't have anything for that. Yeah, I don't. It's too complicated to try to even get into the entire arc of it, because that might have something to do with the atoms themselves. See, it gets a little. See, it's almost like you're creating a bunch of ions. You are creating ions. That's why it's blue, by the way, because you're ionizing the atoms. So that might be part of this also. But I don't want to get into that. So you can just see that this magnet, he keeps a certain distance, and it really fundamentally, like I said, if he was much higher and much lower, then you might get a better picture of the bowl. But the real point is what he needs to do is get much closer, because then as he pushes in, you'll see the beam not only go down, but then you'll start to see it go this way. All right, because there's no real doubt of the truth. All right, that there is a repulsion. So here, let's play this a little bit, because it does have some.
See that the force is not up, it's down.
See, but you can see that it's now down and to the left. So as much as he's saying it's down, I don't think that's down in the center.
So what's wrong? Electrons have negative charge, which flips the direction of the force. So the magnetic force law does work here.
Well, now he's just doing for
a charged particle that is moving in a magnetic field
I want to get to the one right in the face.
Force, which is the fundamental magnetic force.
All right, it's not
the force is given in general by the charge of the particle times the vector product of the particle.
So this part, he doesn't even have the magnet. He's obviously using the electronics to bend the beam. So, you know, we're seeing that the beam is easily deflected. The electrons are easily deflected. All right, so here's the one, I think, where he goes right into the face of the beam. Yeah, okay, this is it. So again, this looks like, oh, wow, how come that didn't bend it at all? All right, so one thing to understand is when they have a cathode ray tube, they're not quite like these tubes. All right, they actually do have a screen on the surface, an anode. And so when they bring a magnet into a TV screen, it has a big anode screen right across the glass. So when you bring a magnet in, you're magnetizing the whole screen. You're magnetizing a big hunk of metal. You're doing Lenz's law. And so that's part of the reason why the electrons react more aggressively, is because you're using the magnetism of the anode, okay, to screw up the pattern. See, there's details to all this stuff, and nobody really goes into any of the details. Nobody pays any attention to details, and they're important details.
Are parallel.
All right, so it's going to go right into the face of the beam.
No deflection.
All right, now he says there's no, but you can see some kind of weirdness happening, I think. Let's see.
There's no magnetic
there,
force.
You see a little movement there. You see a little. So he says no, and then they cut off the film. So the point to understand about the coming in head first is yeah, these are really accelerated electrons. So the ones that are moving towards the magnet are moving at a very high velocity towards the magnet. So it's not like you're just deflecting something, like pushing something that's not pushing back. On those electrons, he's trying to push them back. He's pushing against their forward momentum, and he's doing it at a point where you can't see the beam anymore anyway, right? Because it hits the glass, and I think the glass is opaque to the electrons anyway, so the electrons are being destroyed. So there's a limit to how and he doesn't go right up to the glass. There's, truth again. So you can't see the real full strength effect. So I guess I would argue if you took a neodymium magnet and put it right there in front of that beam, you probably would be able to get the electrons to decelerate enough where you'd see a gap. But the point is they don't necessarily deflect sideways, right? I mean, if I'm putting forward resistance to something, it doesn't always have to go like it leaves sideways. The whole thing could bulge. There's lots of things where the force can go, but we're talking about so the force is pushing the electrons. Remember, I told you the little bits are pushing them. So there's a bunch of that force coming in this direction. So that's the force you have to overcome. So let me just draw that real quick so you understand it. See, there's just subtleties, but they're really important. I mean, you just can't just gloss over this crap, and they just keep glossing over it. So as I was saying, see, there's a bunch of force coming with these electrons. So all this stuff, force, little photons, little energy bits that are actually pushing the electrons along. And so here you are with your little magnet, and your little magnet has a little tiny bit of force. All right? So you kind of can get the obvious fact here. These electrons are being pushed by a very fast, high voltage amount of force. So it's a lot of voltage, which means current. There's current pushing these electrons. The current is in this stream of force pushing these electrons. And you show up with your little tiny magnet, and you're saying, well, why doesn't this beam stop? I mean, you know, I'm pushing my little tiny beam onto those electrons. Why doesn't it stop them? So if I did an analogy, I could say you could take a very strong laser beam, and let's say you had a piece of paper, a little ball of paper, and we could move the piece of paper with the laser beam without burning it. You know, just pushed it. And then you sit here with just a common little, you know, flashlight and shine your flashlight at the paper thinking you're going to stop the paper's movement. You don't have any chance of stopping it, right? You can sort of understand because that has so much energy behind it. See, it's not so much you being able to stop the electrons. If the electrons were just free and they didn't have any voltage behind them, that is, they don't have any there's no force still moving with them at the speed of light moving, okay, still coming from the emitter. The emitter's emitting a bunch of light with the electrons, and it keeps emitting the light, and the light's going much faster than the electrons, right? So the light's going whoosh right past the electrons, but it's hitting the electrons also. So that's what you need to understand. So there's a lot of it coming out. Big beam of light that you're not seeing. The infrared radiation, whatever you want to call it. A huge amount of photons are pushing the electrons. And here you show up with your little tiny, lame little flashlight. And you're going to say, I'm going to push it harder this way. You're not going to have any chance. But yes, if you want to push it sideways, you got a chance. Pushing against the motion, no chance. Yeah, I think that's probably enough just to point out that all these experiments have explanation and they have function, and there's details in the function. There's a ton of details and nobody's paying attention to the details. Again, we can just go back to the, you know, I love this video. I really do. Just because it shows something. You can see here that these electrons really aren't making it for a second round. They're not really going around and around and around and around. Somehow they're losing their velocity. Somehow they can't be part of the experiment a second and third and fourth time around. They're not magnifying the beam. The beam doesn't get any brighter as she turns it into a circle. She can't make it conserve the energy. The energy is being lost. The electrons are decelerating. Something, okay, is decelerating the electrons. And so these are important little details. Nobody pay attention to. Who knows? Details, details. But that's where physics goes wrong. Is it says, oh, this looks like. This is what this looks like something. This look at that. That looks like something. It looks like, you know, and instead of saying, okay, that's not good enough. Okay. The real story is more than what it looks like. Just like the ferrocell is a lie, even the iron filings, it looks like. It doesn't matter what it looks like, okay? Because what is actually causing it to look that way isn't like what it looks like. Yeah. It's like you have footprints in the mud, and then they collapse, and they do this, and they don't look like, they look like something, but there's something else. Because of the distortion, because something happened, because it's just a, you know, it's an optical effect. You've been fooled. It isn't what it looks like. You know, so many examples. I should be able to come up with them. You know, in the real world, you know, all the times you could be fooled by optical illusions, where something looks like something, but it isn't what it looks like. All right, so that's probably enough. Love this experiment, though. Love it. Very cool. Anyway, so yeah, I think I answered your question. I still believe there's a motor force. Okay, so there will be a tendency for there to be a bias. The right-hand rule isn't complete nonsense. It's just so subtle. Because it just has to, again, to do with the fact that, I'll draw a picture of it. the fact that the force through in many circumstances is when it's being created radially and it's mixed, that I've sort of pointed this out, that it's the force is being like this, it's coming out, and it's, especially in some circumstances, it's mixed force. Okay, so it's so, and this is the polarity of the force, but the polarity of the force is dictated by the fact that there's certain rule about, there's no first, there's a red line and then there's a blue line on the other side of it. Okay, that's not how it works. There is no center. There's a blue line and then there's a red line, and the center is here. So there's always a prejudice on one side. One side has one extra red line, one side has one extra blue line, and that's the trick here, is that that's how the circle works out, is that if to make the circle, there's always a bias on one side. One side is always one blue extra, and one side is always one red extra. So that's the rule of this pi, you could even say, right? The pi means there's one side has the straight center, one side has the fork, and that's the rule. That's what's causing the bias one way or the other. Blue, red. Change the polarity of the voltage, red, blue. It's that simple. That's the right-hand rule. All right, now that's enough. Okay. So keep it long and mostly simple, unfortunately. Okay, till next time. Yeah, really sorry, it's too much content, but it's physics. Physics takes explanation, especially when it's been done so badly. And again, I'm not saying I'm doing it really well. I'm just saying these are just a little bit of analysis. You start seeing these possibilities for an explanation, and they just don't do it. The physicists just don't do it. They don't do any analysis critical of their experiments, or that wish to understand exactly how the thing functions step by step by step. They just don't care. They want to prove a point. They don't want to dissect the truth. I mean, their experiments are for display purposes only. They're not for educational purposes. They're for propaganda purposes.